lecture. Okay, so this is NMOS layout with the body connection. This is as follows. This is a P substrate. This is P plus, from where we are taking the port terminal body. So it is not going at the bottom actually. It has to be taken at the top side. So in a chip, it should go other side. Same way, source, drain, and gate. We already talked about this. Right? This is known as the channel. Sometimes channel length. That is in L, and back side you will see something like this. This will be the width. So looking from top, if I am looking from top, how the layout should look like. So layout should look like as follows. Generally middle area is little bit extended one. This one is gate. This one is, I'm writing N plus, and this is source. This is N plus and drain. And if you look at here, this is a P plus, which is giving me body or substrate or bulk, whatever name you want to call. All are synonym to each other. Different books are following different names, right? Behzad Razavi is using body, right? So this is how the layout look like, right? Looking from top, this is the top view, and this is the only view available on Cadence software if you are going to draw the layout. Looking into CMOS layout, which is combination of NMOS and PMOS both together, then looking into one side, if you look at this is NMOS, which is exactly what we have drawn over here. But for PMOS, you need one N-well over here. So N-well, because we need to make one body over here. So N-well, and then N plus, and I am taking the body of, this is body of PMOS, and this is body of NMOS. By the way, for CMOS technology, substrate is always like the P substrate over here, right? Sometimes some has triple well is also there, right? You can make like this also. Sorry. It is like this, right? So can you see there are triple well are there? So it's a triple well technology where P plus and N well. So you are depending on the foundry who is designing or fabricating the chip. They will tell you that whether it's triple well, dual well, or whatever they want to make. Right? Accordingly, this will come. Right? So X well is triple well, right? So it depends. Sometimes this is CMOS. That's why it is like this. For different technology, it's a different steps. Like FinFET will have different, FDSOI will have different. So this is general for any CMOS technology. Now, that's so there is no problem, right? If I want to draw the layout of this one, it will look like this one. So with the red color, I am drawing NMOS, and with green color, I am drawing PMOS. Understand? But if you're looking from top, P substrate has to be drawn separately because it has been actually grown inside P substrate. So I'm making this dotted line. It represents N-well. So that's why it is always there. If you are studying, let's say, digital MOS or where stick diagrams are there. So stick diagrams have notations like this. So this indicates it's an NMOS, and this indicates it's a PMOS, right? Depending on what notations you are following, and accordingly you can use it, and you can draw the stick diagram, and you can, there are certain algorithms are there using which you can sequence which NMOS has to be first, and you can do the routing, and you can make the required layout. So that is very much useful. Sometimes some people are also using such layout techniques. So this stick diagram for analog also, but generally analog designer are separately, they are not using stick diagram traditionally, but yeah, it's up to you. If you like it, you can use it. Okay, but this is the standard notation. When you are studying digital MOS, then this will be there, right? So stick diagram will be there. Somebody has studied stick diagram earlier. So stick diagram origin is from here. Let's assume that if I want to make an inverter which look like this one, if I want to make the stick diagram first, so then I have drawn, this is PMOS, this is NMOS. So you know that they are interchangeable. This is drain to drain, right? So drain to drain. This is one connection. This is out, let's say. Then gate to gate. Then right, and then up one will go to, this goes to VDD. This goes to ground. Similar layout you can make it. Layout looks like this one. So, right. So this is called stick diagram, by the way. Anyway, you will study this in detail in other course, which is not part of this one. So let's go to our course where little bit of device physics, not too much of device I am going to use. So if we have an NMOS where gate voltage is connected to some voltage called VG, drain is connected to 0.1 volt, source is connected to ground, and P substrate is connected to ground, right? So this is body which is connected to ground. Generally, in principle, we are making VBS equal to 0. Somebody knows why we are doing this? VBS equal to 0? To avoid leakage current. Okay. Anything else? Sorry?
So we don't have variation in threshold voltage.
Yeah. So two answers. One of them is leakage. That's also true. And body effect, where you do not want threshold voltage to be changed or a constant threshold voltage. Generally, for VTH equation is there where if VBS is 0, then and then VTH equal to VTH, which is giving in foundry something as a function of somewhere VBS is there, something is there. I don't remember the exact device equation. So this VTH 0 is the one which is defined in DC model parameter. Do we understand this? Punit, do they understand DC model parameter? Okay. So, do you understand? So, what have you done in your laboratory? Huh. A little bit louder so others also can hear you.
In the previous lab, we designed the NMOS.
Okay, so you have done this one, NMOS, only NMOS, and then
And PMOS.
PMOS is on top. Inverter. You did this inverter.
NMOS and PMOS different.
Okay. What they have done? Okay, so you have used any load or anything? No load. So what have you done? They have added here voltage. What about VDS? Is it? So for anything which you are doing, right? Okay. Now certain questions. Now for your laboratory, you did it. So which technology have you used?
TSMC 28 nanometer.
28 nanometer. TSMC 28 nanometer. So is it CMOS technology or have you used NMOS? You have used, but what is the technology name? So it's CMOS, right? We have only TSMC CMOS because we have ST's FDSOI 28 nanometer is there. Like for that one, BCD technology is there, right? XFAB. Anyway, so TSMC 28. Okay. Have you checked what is the threshold voltage?
Sir, I
2.4. Okay. So before that, then it's
2.4 or 0.6.
what is VDD? What is VTH?
0.4
Hmm?
to 0.6.
How do you know that it's 0.4 to 0.6 is a big number?
Actually, I have asked this much.
476 millivolt आपने देखा नहीं? 7 पैरामीटर.
These numbers has to be on your fingertip. Look, I want you people to work on this technology throughout the semester so that you know the whole technology and these numbers has to be on your fingertip. Then and then you can design the things. You can't say that 0.4 to 0.6. You should know the number. Look, as you are working, so I don't know 470.
476 millivolt.
So 476 millivolt, right? By the way, other than that, GM, what are the things? You can find out.
सर ये सारे पैरामीटर हमने बोला था कि आप कैलकुलेट करके लाओ.
Okay.
Km, Kp, lambda.
Okay. So you found out all these. You found out all this K and Kp. I believe everybody understand K and Kp all this, right? You understand or Abhishek? Okay. What could be the Kn and Kp? Okay. Let's go this way. Do you know the IV equation? What is the IV equation for NMOS? ID is equal to
Yes, sir. There
mu on Cox W by L
so that combined.
VGS minus VGS square. So
That combined terms.
right. Okay, so this is right. Sometimes high K devices. If you go to your device class, then they will talk about high K devices are there. Right. So anyway, so the most important part over here is without how do you know that what you achieve is correct? So did you achieve exactly 476 millivolt? Everybody achieved 476 millivolt or something else? But how do I know that that's the correct one? There is always two things are there which you need to read. One is called DRM. That's equal to Design Rule Manual. Please share that. Puneet share with these people. Right. So Design Rule Manual DRM. You can also find out it must be available in wherever the path from where you are, launching cadence. It must be there somewhere. Path is somewhere fixed where cadence and then documents. In documents you should find out somewhere. So that this will tell you everything. This is like we don't call data sheet, but we call design rule manual, which has everything is written for that technology, right? What is allowed, what is not allowed. There are many things. Once some rules are there, those things are already mentioned in that. Where some of the key parameters are also mentioned, right? Like these parameters. But as an engineer, I am not going to read this manual code, right? So there is something called all these parameters. We are going to call that name as device model parameters. This is the name of these parameters, which you should know always, or they have to be on your fingertip. If you know these parameters, then things are very very easy, and these are written in device model parameters. So in AD, just correct me, Punit, if I make any mistake, because from many years I am not using AD. In AD, tools are there, and in tools model parameters, correct?
Sir, setup and model I think.
No, not that one. Go to tools, you again check tools, then you will have model parameters. You please check and let me know. If I am wrong, then I'll correct it next time. So in AD, maybe the last one in the box, last one is tools. Open it. Then when you will open it, some .psf file will open. That PSF file has everything. Those things are written over there. That these are the DC model parameter. Understand, these parameters do not change generally. These are for the unit size of the transistor. They will not change. Means 28 nanometer, 1 volt, VTH. They will write down VTH 0. As I was saying, VTH 0 plus some VBS is there. So that voltage and other things are written, right? Whatever GM, KM, KP, many things like even gamma factor, that body effect coefficient, and many things. If you want to understand its unit, but units won't be written over here, by the way. There are no units. So how to know what is the unit of that? How do you know that it's 476 millivolt only? How to know this? But how do you know that it's volt? No, nothing is standard. How do you know sometimes it's millimeter or centimeter or micrometer or nanometer?
Small.
Like TOX, oxide thickness. So something is written, let's say. What is the unit of this one? If you are guessing, how do you know that it's correct only?
You can calculate by COX equal to epsilon OX by TOX.
But TOX is required, right?
So
You don't know COX. You don't know COX. You have to calculate COX. For that, you need epsilon A by TOX. I know area, I know epsilon, even epsilon of silicon also. But TOX is not known to me. How do you know that it might be centimeter also? Understand? I'm just giving you an example, but let's say Kn. Now tell me, what is the unit of this one? Is it volt centimeter or volt micrometer or something? Right? What is that? Here, there are lots of things are there. So, how to know that? Okay, if somebody knows. Any guess? Google. Google.
Telling the software.
Hmm?
We're telling the software.
How to tell it?
This side.
No, this is, look, we need to know the unit. Unit is more important, right?
Lookup table is it.
Hmm?
This is my guess. This is a
No,
lookup
there is no
table.
lookup table. There is no lookup table because it's a device DC model parameters which are not changing. Understand? But unit might be changing. Understand? Sorry, units are fixed. Numbers might be changing. I am saying units are changing because this is happening from many years. From even when Gordon Moore was there. From that time, this DC model parameters are available in all the simulators. So their units were fixed, and these numbers are changing. Understand? Right? So they are writing accordingly. They are not changing the unit. So how to see the unit? So that is, let's again understand. If you are simulating this one, what are you simulating actually? What are you simulating? Are you simulating this symbol? There is no symbol, right? Yeah. As an engineer, we are, simulating these equations, right? What you have studied in circuit theory, it's all about its equivalent transfer function, right, or its equivalent IO characteristic, right? So we are simulating this one. By the way, the equation what is written is not fully true. It's only for the transistor when it's in the saturation mode of operation, right? For other mode of operation, this is changing, right? So then this equation does not hold, by the way. So in all different region, this equation is different. For triode, it's different. For even in cutoff, it's different. So all equations are different. So when you are simulating this for a given region, then you need these parameters. Understand? Right? Which are actually fixed parameters. Mu n, Cox means indirectly Kn. In the case of NMOS, in the case of PMOS, it's Kp. And VGS is also again fixed. VGS also you are checking because it's a variable over here. But that will be known only after running the simulation. Even this VTH will also come after running the simulation, because if there is body effect, VTH might be changing. I'm not talking about VTH 0. VTH 0 is same value which is written in the DRM. Whatever written in the DRM, it's only possible if you are not doing anything with the transistor, right? It's a normal, like WL and everything is normal. If it is changing, then accordingly the things will change. Those are not the model parameters, right? Those are not DC model parameters. Those might be the different parameters which you can run it for, after transient, after whatever analysis you are running, AC analysis, or so then you can see those things. So those are there, right? So when you are simulating, you are simulating this one, right? And you are plotting it. Last time we talked about it, that what exactly we are doing at the back end, right? So other than that, whatever is happening, that is what actually you are seeing, right? I forgot what I was saying from here. Units, yes, sorry. So units. So now after running this, look, by plot you can see anything, but understand, let's assume that you are in 1970, not today, in 2023 and 1970, almost between 50 years. What exactly they have done? We are simulating this. If this equation is so much simple, then there is no cost at all. Understand why we need various engineers we require. One of them is device engineer, compact model engineer, maybe design engineer, layout engineer, right? Maybe front end and so on, like verification, and the people will be there. So role of these engineers, one of them is device engineer, might be fabricating the your chip or the device. It is like mostly on physics and chemistry side. This guy is the one who is playing very important role between fabrication and design. If he is not there, then there is no possibility to simulate this particular transistor. Every year or every 1.5 year, when transistor is changing, this compact model engineer has to give us the new model, right? So if you remember, we also talked about Ohm's law, right? V equal to IR, but that is only at room temperature, right? At room temperature. However, if you change this equation will change. But still I am saying V equal to IR at room temperature. This is the thing which is happening on sitting in this laboratory. If it is like the same thing, if I am taking it to, let's say, moon or Mars or any place which is not Earth, this equation might be changing, right? One has to check that. This might be correct, but not at 27 degree. It might be at some other degree, right? So those things has to be checked. And compact model engineer, what he does, he takes the one device from device engineer, and he will again check everything. Then he will use his known mathematics, and he will make some fitting parameter alpha, beta, gamma, whatever he likes. In addition to these things, and this equation might be much more complex than what you are seeing right now. For different temperature, different process, different voltages, it's changing. So then that model is given to you, and that's why whenever you are running the file, if you are seeing somewhere input.scs has some problem, you must have seen this kind of error. Have you seen somebody has seen error first of all when you run the simulation first time? Have you seen the error?
Yes, sir.
What was the error and how did you fix it?
So we pinpoint the, we see the error number.
What? No, not number. What was the? How did you fix it?
So like what I done with the circuit simulation. So I pinpoint that voltage, then.
Understand, there are two things. Warnings and errors are different things. Error will not allow you to run the simulation,
Yes, sir.
and warning is it will run the simulation but with some warnings.
Yes, sir. So I fix warning.
Not warnings. I'm saying if you have seen error, somebody has seen error or no. Punit has given you good leadership, but in my opinion, you should.
Model library से कोई
No, karo. Let's wait. You have to remember. Otherwise, you will never able to fix this. This is very difficult error sometimes if you are not able to fix it. When I did first time, like almost 20 years back, first time when I run the cadence and I seen same error, me and my friends almost took 3-4 days. My seniors are also not telling me what is going on, right? So this error is the one where it looks like this one, that input.scs has some problem. This kind of error you will see. If you are seeing such kind of error, is actually you have not added the model library. So model library path addition has to be done in AD. In AD maybe second or setup. In setup there has to be model library. In AD go to setup. In setup go to model library, and there are various libraries you have to add. Those libraries are this transistor. If you are taking from TSMC 28 nanometer, how does it know that this is 28 nanometer equation I need to follow, right? So that you need to give, and I believe everybody knows slow, fast, all these things. Yes or no, Abhishek? So generally what happens when you are running any simulation or anything, let's go this way. This is very important thing, unfortunately not mentioned in any book, but this is the thing where people are working and day and night they are working, all electronics engineer. Very important thing is, have you heard that BJT, if you are purchasing from the market, its beta is something like 200 to 300. Have you heard about this, right? Right. So look, beta is from 200 to 300. It's quite a big variation, because IC equal to beta IB, right? So current is actually changing by factor of 2 and sometimes factor of 3 if you have the different beta. In the same laboratory, you can't guarantee the same beta will be there. So this is called this BJT. When somebody has made it, he is not able to make the same BJT, identical BJT, right? Same is true for all other things. So if I am saying I am making this transistor, here it looks very beautiful, n plus, and things are fine. But in reality, it does not look like this one. If you remember, I told you that we should have this kind of transistor, but it will look like this one. Something like this. And these are not the line, it's like you are depositing something. And believe me, it's a very crucial job. When you are learning this, then you will understand there is something called CMP process. So that's chemical metal polishing, right? CMP is Punit. CMP is chemical metal polishing, right? Fabrication process. So that's the last step. If you look at the chip, on top of that chip, these are different layers. So at the end, it looks like this one. So it has to be polished and it has to be made, them flat. So then doing all this will not give you guarantee that one chip look like this one, other chip might be something like this also. Anything can happen. You might have some variation. So it is very difficult to make such kind of chip exactly identical, and going at the low technology node such as 3 nanometer, it's becoming more and more difficult, right? So here the point is, this is all happening because of fabrication uniformity. It's not at all reproducible, but we have invented one term that if whatever we wanted to make, if the transistor is same, we call that transistor as typical, that it's exactly ideal one which we wanted. Another one is slow and another one is fast. Note that all these terminology is coming from where, those who knows why we are calling slow fast, what is the meaning of that?
Sir, the switching speed.
Nothing is switching right now. Okay.
Time period.
Hmm?
It's a time
Threshold.
Threshold voltage, right? So it is about threshold. So if transistor becoming slow, means it require more voltage to make it turn on, and for fast, it's becoming faster. If it is typical, the threshold voltage which you wanted, or whatever the VTS 0 is written, note that that is for typical corner. We are calling this one as corner. For CMOS technology where NMOS and PMOS are there, so SS, FF, TT, SNFP and FNSP. There might be some different name also depending on technology. These are the names for 130 nanometer or even 65 nanometer. These are the names. Slow means first one is NMOS and second one is PMOS. Slow and slow PMOS, fast and fast PMOS. Typical both NMOS, PMOS, slow and fast PMOS, and fast NMOS and slow PMOS. So this is the way we finding out 5 different corners for my transistor. So this is happening because of fabrication. Fabrication non-uniformity is lead to have 5 possibility, right? Other than that, there is a possibility that the temperature, whatever consumer electronics we are designing, understand sometimes you are sitting here where temperature is going, let's say 0 -1 degree very easily. If you go to Delhi, it goes almost like 40, 47, 46, right? Or same mobile works in Dubai also, same mobile works in Antarctica also, right? At least it works. Signal is different thing, okay? I'm not claiming our signal, but what we are saying is all consumer electronics has to work on this particular range. This particular range it has to work. So this is agreed thing that all consumer electronics we have to make sure that it has to work between -40 to 125 degree. And same way, voltage is another thing where whatever the VDD is given, you might have some plus or minus 10% of going up and down is also possible. So this one, which was with process or with fabrication, we can call that one as process corner. This one is voltage corner, and third one is temperature corner. Combining it all, we call PVT corners, process voltage and temperature. So over process voltage and temperature, if we are taking, let's say 10 from here, 3 from here, and almost from 5 from there, right, for transistor. So you need to run this for almost like 150 corners. But understand, in our design we will have resistor, capacitor, inductor if it is. Each one of them will have 3 corners, as we know: slow, fast, typical, slow, fast, typical, slow, fast, typical. right? Everywhere resistor value can go high, low, all these mean, max. That has to be multiplied from here, and those many number of corners you need to run, and you have to check on each corner the circuit should perform as it is required. You can't say that it's, if it is one corner is failing, means when the chip is coming, same corner is coming. That's Murphy's law, and that is what happening, right? That, sometimes I actually did it intentionally when I was tapping out my first chip. So I kept one circuit which was tuned for all the corners, and one circuit where 2-3 corners it was failing, and the second circuit which I made it for failing for 2-3 corners, actually it didn't work when I made the real chip. So that happens. Even my professor also told that it does not work. It's a Murphy's law, and it happens only, right? So anyway, so make sure that your circuit has to work on each and every corner, right? This is what all designers are doing when they are sitting in the, you know, in office from morning to evening. So inductor is generally not there, but so almost like 1,200 corners, right? More than 1,200 corners you have to run, and you have to check. So if one corner is taking, let's say, sometimes if full chip is taking, let's say, 1 hour, then 1,200 can take 1,200 hours. Sometimes we are using multi-core and many things are there, but yeah, you have to do all these things and make sure that each corner it has to work. But this is just a schematic, by the way. What you have done is for schematic. Later on, once schematic is working, you check for layout also. And layout, you are getting all the parasitic effects, and you are saying that PAX simulation you are running, parasitic extraction simulation, right? PAX you will run it, you will learn it in other course in digital IC design. So if you want to follow, there is no problem. If you want to learn without both the courses, I already recorded. I taught digital mouse LSI earlier, so it is online. After learning Virtuoso, you can do it if you want. There is no problem. And still, if you have any doubt, you can ask me or my TA. These are the just tools, so it's not a big thing. So parasitic extraction, and you just add these things in schematic, and then again run 1,200 corners, whatever time it takes. Once this is done, then whatever the worst corner you wanted to achieve, let's say for a gain of 100 dB, and you achieved the 100 dB gain at, let's say, slow minus 40 and VDD minus 10%. You achieved your, this was the corner where you achieved this gain. Other corners, it is more than 100 dB, right? So this is a worst case corner. Then I am going to run something called statistical mismatch analysis, or the Monte Carlo analysis. So gain with respect to different number of occurrences where all transistors are actually change their GM and other things in a Gaussian way, right? So that is what actually happening at the back end. When you run it, you will see that this kind of output will be coming. Mean value is mu, as you know about mathematics and all. So these are the same terms. This is sigma, right? And 6 sigma, right? So sigma is deviation, standard deviation, right? 3 sigma, 6 sigma. So most of the companies like to see their things working at 6 sigma. If you know that, so this is same 6 sigma, that it is all the results. So 99%. So that is what we are also checking for all our designs, including our op-amp or whatever you are designing. So this is what we have to do, and this is what you need to learn to our this course. Right? I'm not sure whether you can learn layout or not. So it's up to you. But there is other courses also there, digital, where maybe more focus will be on layout and other things. But if you want to learn it from here also, there is no problem. I don't have a problem. Okay, there is not much things in that, right? Okay. So this is what PVT, no problem, absolutely fine, right? PVT, process, voltage and temperature. So those has to work from minus 40 to 125, and for all the corners it has to work. And believe me, like when we are testing the circuit, we are keeping it in oven and we check that. That is how it has been tested, right?
Just one question.
Yeah,
What is corners?
yeah. Corner is one possibility point. We are calling it corner, right?
The one possibility of transistor.
One possible. So there are temperature possibilities are going from minus 125, minus 40 to 125 degree, right? So in between, I am taking, let's say, 10 points. Those 10 points are 10 corners,
Yes.
right? So this is specifically to VLSI engineer, term. Thank you for asking, but yeah.
So why the temperature corners are so extreme? From like minus 40 to 120.
Because we can use it in even in car also, right? Harsh environment or whatever we are running on earth, it's on consumer electronics. Sometimes it goes that temperature. Sometimes the temperature around you, it's actually higher. That also happens. Not actual mobile is taking temperature till 125, but outside temperature is also high. That might happen, right? So this is a standard and agreed by all other people, and then we reach here.
Sir, can it be that certain chips can go to 125 and certain do not? Like the processor in our
So then we
mobile-
will say that it's not working at PVT corner.
So a
Yes.
chipset that will be used in a car.
This is for consumer electronics. Even cars will have even more harsh temperature than what is written over here. It require even sometimes 300 degree, where your silicon don't work. So it depends. I'm telling you, this is for consumer electronics, all electronics. Even if it's not VLSI, anything, any electronics has to be designed between minus 40 to 125. This is the standard thing.
So harsh is military
This
grade.
hmm?
So harsh is military grade.
Harsh is military grade. Cryogenic is also there below minus 40, right? Like minus 120. Or those are for the cryogenic temperature. One is for harsh, and this is for consumer electronics. Right? So this is the thing. So
So the number of PPT corners are fixed or
you can increase. You can increase. Right? Instead of 10, you can take 100 also. But you understand that much time will be wasted. Right? If I know that I am not going to, use this in beyond that particular temperature, then also you can, drop that temperature. Like sometimes we are running from minus 20 to just 100. These are the requirements given by companies, right? As you are saying. So this is general statement, minus 42 plus 125 degree.
so generally the processor that we use in our CPUs.
This is qualifying this range, minus 42 plus 125. If it is failing at any one of that, they will not give you as the product. They will say that this is not. There is one term called yield. Do you know yield? So how many chips are working? All chips has to work from minus 40 to 125. Right? If they are not working, then either they will not claim that temperature, they will claim something else on product, that box, or they will say that, yeah, you please, if you want something made in China, they don't care. Okay, I should not say this. This is recorded. Right. But yeah, they sell very good products in China, right? Then they give different product to other people, right? So, like that is how we define yield and any other thing. But this is the standard. If you are following this, it looks like okay, you are following what is agreed by all consumer electronics people. So the G, TI, all good companies, they are following this, and they are also saying that our product is Six Sigma, right? You heard about it then. From minus 40 to 125, at worst case they are checking it and then they are giving this product. By the way, what they are claiming is for, whenever they have, like, let's say 100,000 mobiles they made, then they are checking how many mobiles are working, and those working mobiles are only given to you. That is the meaning of Six Sigma. Three Sigma might be like something. Some of the mobiles are failing, but still they are giving you. If it is here, that is the thing. That's all for today. So when you are doing cadence, please look at those things. Okay, before signing off. So the important thing is the compact model engineer who is writing these equation, and compact model engineer actually team. There is something called BSIM is very popular. We are running that Berkeley simulation model, right? Berkeley is from same UC Berkeley. So there is one group who is writing this BSIM manual, and in BSIM manual those units are written. We are following those BSIM manual units, right? So those are written there. You can download it from UC Berkeley website. It's freely available. That PDF you just download, and in that when one big table is made, even some of the parameters which are not known to us, like ABCD or some, so those things are also written there. Alpha, beta, gamma, fitting parameter, these parameter, that parameter, all those things are written there, and their units are also there. Use that units and you can find out the exact value, right? Okay, so that's all for today.